You know, we've been promised the holy grail of energy for as long as I can remember. Imagine it. The power of the sun and stars, right here on Earth. Clean, safe, basically limitless electricity, all from something as simple as a glass of seawater. We're talking about nuclear fusion, of course, and it has always been the ultimate promise.
But there's an old joke in the science world that goes along with it. If you've been following this for a while, you already know the punchline. For something like 70 years now, commercial fusion power has always been just 30 years away. It's kind of become the ultimate boy who cried wolf of big science.
So, what gives? I mean, why is this so unbelievably hard? We managed to split the atom, we put people on the moon, we've built supercomputers that fit in our pockets. So why can't we just smash some hydrogen atoms together and, solve our energy problems forever? Well, today we're going to look past all the hype and get into the brutal, nitty-gritty engineering reality.
All right, first up, we've got three huge hurdles to get over. The first one is what I like to call the invisible bottle problem. On paper, fusion sounds pretty straightforward, right? You just slam atoms together with so much force that they fuse into one, and in that process, they release a ton of energy. The real challenge, though, is creating the insane conditions you need to make that happen in the first place.
And when I say insane, I mean it. To get atoms to fuse, you can't just match the conditions inside a star. Nope, you have to blow them away. We're talking about reaching 150 million degrees Celsius. To put that in perspective, that is 10 times hotter than the core of our own sun.
At temperatures like that, matter it isn't a solid or a liquid or even a gas anymore. It turns into this fourth state of matter called plasma, basically a super hot, electrically charged soup of atomic bits and pieces. And here is the fundamental problem. If that plasma touches literally anything, the reaction dies instantly, and whatever it touched just vaporizes. There is no material on planet Earth that can hold it.
So, how in the world do you hold something you can't touch? Well, the brilliant answer is, you don't. You build an invisible bottle. The solution is to trap and suspend the plasma inside these ridiculously powerful magnetic fields just floating in midair inside these huge donut-shaped machines called tokamaks.
Now, I love this analogy because it really gets the point across. Trying to contain plasma with magnets is like trying to squeeze a balloon, but that balloon is filled with angry, wobbly jelly. And you can only use rubber bands to squeeze it. And oh, by the way, you can't ever actually touch the balloon. This plasma is so unstable that just keeping that magnetic squeeze going for a few seconds is a massive, world-class achievement.
Okay, but let's say we do it. Let's say we perfect our magnetic bottle. We're good to go, right? Nope, not even close. We immediately smash into our second major problem, a complete and total material science nightmare. And this one is all about the very walls of the reactor itself.
See, when fusion happens, it spits out these incredibly high-energy particles called neutrons. Think of them as subatomic bullets. Now, in a power plant, you actually want these neutrons to slam into the reactor walls. That's the whole point. That's how we capture their energy as heat to boil water and spin a turbine. But these same neutrons are also incredibly destructive. They're like a constant sandblaster on an atomic scale.
So here's the impossible task. The reactor wall has to take this constant beating, this endless bombardment, for decades without breaking down or becoming brittle. We need to literally invent brand new materials that can handle this kind of abuse 24/7 for the 40-year lifespan of a typical power plant. And the simple fact is, right now, those materials do not exist.
And that brings us to our final hurdle, and this one might be the most misunderstood of them all. It's the tricky energy equation. Because for fusion to actually work as a power source, it's not enough to just make fusion happen. You have to get more energy out of the whole system than you pour in to run it.
Now, this is where a lot of the news headlines can be a bit misleading. When you hear about a fusion breakthrough, they're almost always talking about what's called scientific break-even, and that means the fusion reaction itself, the little puff of plasma, created more energy than was put directly into it. And that is a huge scientific deal. But for a power plant, what we need is engineering break-even. That's where the total electricity the plant sends to the grid is more than all the electricity it sucks from the grid to power its own gigantic lasers, magnets, and cooling pumps.
This chart right here shows you the catch perfectly. It's from that big recent experiment at the National Ignition Facility. And yeah, you can see the fusion reaction did produce more energy than the lasers hit it with. Awesome. But then you see the other bar. The massive amount of energy it took to power up those lasers in the first place. It was hundreds of times more. We are not even in the same ballpark as engineering break-even yet.
So, with all these mind-bending challenges, where does that leave us? Well, I think it means we have to look at fusion for what it really is. It's not a sprint. It's not going to save us in the next 10 years. It's a multi-generational marathon.
And humanity's biggest bet on that marathon is a project called ITER, which is being built right now in France. It's this gigantic international experiment, and its one and only goal is to prove that a net energy fusion reactor is even possible. And like a lot of these moonshot projects, it's billions of dollars over budget and years behind schedule, which if anything just proves how ridiculously hard this all is.
This timeline really puts the whole journey in perspective, doesn't it? We started with just the theory back in the 50s. Now here we are in the 2020s running these massive, complex experiments. The next big step, if we're lucky, is proving it's viable sometime in the 2040s. But actual commercial power plants lighting up our homes, realistically, we're probably looking at 2060 or maybe even later.
So if there's one thing to take away from all this, it's this. Fusion is not vaporware. It isn't science fiction. The physics is real and it works. But turning that physics into a reliable power plant that can run for decades is quite possibly the single hardest engineering challenge our species has ever taken on.
So yes, we should absolutely keep chasing this dream. I mean, the payoff, clean, abundant energy for the entire planet, is just too incredible to ignore. But it does leave us with a really important question for today. While we're running this epic marathon for the ultimate prize, what solutions do we need to rely on right now?